Hello chemists, welcome to lecture 44. Let's first discuss some vocabulary for our new unit, nuclear chemistry. Involved in nuclear chemistry is something called nucleons, or the protons and neutrons that make up atomic nuclei. Protons and neutrons collectively are known as nucleons because they make up a nucleus, so they're called nucleons. Also involved in nuclear chemistry is something called a nuclide, or an atom that's identified on the basis of its nucleus's number of protons and neutrons added together. Involved in measuring the stability of these nuclides is something called nuclear binding energy, or the energy that's released when a nucleus forms from nucleons. How this works is the nucleons, or protons and neutrons, when they combine and form a nucleus, will release a specific amount of energy, and depending on the nuclear binding energy, or how much energy they release, that determines how stable the nucleus is. Next, we have something called binding energy per nucleon, which is the binding energy for a nucleus divided by the number of nucleons, or protons and neutrons you have. And this relates to how tightly the nucleons are bound to one another. Now, how this is compared to one another is you have the average binding energy per nucleon in different isotopes in megaelectron volts versus the number of nucleons in the nucleus, which is the number of neutrons and protons. And if you break down this definition, that also is known as the atomic mass, or mass number A here, which we learned in Unit 2. And if you look here, what you'll realize is that when you have an atomic mass, or mass number of around 59, that kind of atomic mass, or mass number 59 in the middle generally will have the greatest binding energy per nucleon, so that's the most stable. In other words, elements with intermediate atomic masses, or mass numbers of around 59, will generally have the greatest binding energy per nucleon, so they're the most stable. On the other hand, nuclides with atomic masses or mass numbers of greater than 59 are not stable, or not as stable as these in the middle, because these are too heavy. And nuclides with atomic masses or mass numbers of less than 59 are not as stable either as these ones in the middle, because atomic masses of less than 59 are for light nuclides, which are too light to be stable. All right, so just make sure you note that. Next, let's discuss Nuclear Chemistry 101. Nuclear chemistry studies the atomic nucleus along with nuclear reactions like fission and fusion, along with the products of these nuclear reactions. And involved in these nuclear reactions in nuclear chemistry is something called radioisotopes, or unstable isotopes with a nucleus that undergoes spontaneous radioactive decay or a breakdown, which we'll discuss in slide 5, which looks something like this. You start with one big one and you break off into 2 or more smaller nuclei, but we'll talk about that in a minute. Next, let's discuss the band of stability, which is a range of neutron and proton ratios over which stable nuclei cluster and exist. How this is done is the number of neutrons for a nuclide is graphed against the number of protons for a nuclide. And basically, depending on what band of stability they're in, or if they're out of it, that can determine the type of decay, which is actually shown by these different color codes here. Okay? Make sure you use this for your homework. But let's talk about this band of stability more. Generally, stable nuclei will exist for atomic numbers or number of protons from 1 to 20. Because from 1 to 20 for the atomic number of protons, these nuclei are stable because you have a 1-to-1 neutron to proton ratio. Also stable are nuclei with atomic numbers or number of protons from 21 to 83. And these nuclei or nuclides are also stable because for these atomic numbers or number of protons from 21 to 83, you have a 1.5 to 1 neutron to proton ratio. So basically any nuclide with neutron to proton ratios of 1.5 to 1 down to 1 to 1 are all considered stable. In other words, if you put it another way, any nuclide with an atomic number of 1 to 83 generally will be stable because you have a 1 to 1 to 1.5 to 1 neutron to proton ratio. All right? However, you also have something called unstable nuclei, which exists for nuclides with atomic numbers or number of protons of greater than 83. And how we describe this is all nuclides with atomic numbers above 83 are considered unstable, radioactive, and thus tend to decay. And why did these unstable nuclei decay? Well, because when the nucleus is unstable, it'll decay and break down to attain a more stable configuration by forming a different element through releasing particles. And this improves the neutron to proton ratio, because if you have an unstable nucleus with this high atomic number and high number of protons, you also tend to actually have more neutrons as well, if you check here. And if you decay, you'll actually lower the number of neutrons because you're transformed to a different element or a different radioisotope. And as a result of that, you'll lower the neutron to proton ratio, and it'll become more stable as a result of decaying to get that more stable configuration. All right, so just make sure you note that. Next, let's go over nuclear reactions. Nuclear reactions involve unstable nuclei undergoing spontaneous changes on their own that alter the number of protons and the number of neutrons, since we know there's nuclear chemistry. And as a result, they will give off large amounts of energy in the process, therefore increasing their stability, because we know that as you release energy, you become more stable from other units. All right, now nuclear reactions are described as reactions that affect the nucleus of an atom, either the protons, neutrons, or both. And two things worth noting for all nuclear reactions is something about the energy, mass, and charge. Generally, the energy, mass, and charge in both nuclear and chemical reactions must be conserved or all three of those must be kept the same both before and after the reaction, because that must be true of all nuclear and chemical reactions. Mass, energy, and charge must be conserved or kept the same before and after. All right, how this is manifested in a nuclear reaction is that the sums of the atomic numbers in the bottom and the mass numbers in the top on both sides of the nuclear reaction or equation must be equal on both sides of the nuclear equation. All right, for example, if you look down here, this example down here really nicely illustrates this. If we look, we have 220 for the mass number of Fr, 87 for its atomic number. Then it actually undergoes a spontaneous change over here to change into He with the mass number of 4, atomic number of 2. Also on the product side, we also have the nuclide A216 where the mass number is 216 and the atomic number is 85. Right, and what you notice here is when you add up the sum of the atomic masses on both sides, 4 plus 216 here and 220 here, they're both the same. They're both equal to 220 for the mass numbers on both sides. Also know that the sum of the charges or atomic numbers in the bottom left corner for each of these elements on both sides is also the same, which is 87, because you have 87 on the reactant side here. And the product side here, you have 2 from He plus 85 for the atomic number of At, gives you 87 on both sides. So the sum of the masses and charges must be the same on both sides for all nuclear reactions no matter what, because that's true for all chemical equations as well. All right, now nuclear reactions relate to changes in the nucleus, either the protons, the neutrons, or both. So electrons can largely be ignored. Do electrons sometimes change? Maybe, but not as often as protons and neutrons do in nuclear chemistry. All right, now what I just showed you here with Fr changing from Fr220 all the way down to At216 is something called a transmutation, where you have a change in the identity of the nucleus because of a change in the number of protons. Since you're changing the atomic number or the number of protons from 87 to 85 here, as a result of changing the number of protons in the atomic number from 87 to 85, you're changing the identity of the nucleus from Fr in the reactants to At in the products. And you're also releasing alpha particles, which we'll learn about later, or helium-4 nuclei in the process. Okay? I'm not going to go over this too much, just know that mass number is the top left number, which equals the number of protons and neutrons. The atomic number is the bottom left number, which is the number of protons, which identifies the element. And obviously, this is broken down for you. All right, next let's discuss radioactive decay. Radioactive decay is the spontaneous disintegration or breakdown of a nucleus into lighter nuclei. So you go from one heavy nucleus that's very unstable down to 2 or more lighter nuclei. And as a result of that, when you break down, you also emit particles, electromagnetic radiation, or both of those. Since you have one particle by itself, breaking down into 2 or more lighter nuclei, along with the emission of particles, EM, radiation, or both. This is also known as natural or spontaneous transmutation because it transforms into another element on its own without any prompting from anything else. And it's also known as spontaneous decay because it decays on its own. All right, now these particles and electromagnetic radiation that can be emitted from nucleus during radioactive decay is just known as nuclear radiation, so make sure you know that. Also, a radioactive nuclide, which is used here, that breaks down from a heavier nucleus into 2 or more lighter nuclei, is an unstable nucleus that undergoes radioactive decay. Note that all nuclides with atomic numbers of greater than 83 are unstable and radioactive, and therefore they will decay into lighter particles and emit particles, EM, radiation, or both. Okay. Now let's discuss types of radioactive decay. For each type of decay, I'll discuss decay mode, what happens, why it decays, each decay's penetrating power, decay mode and symbol, and general equations. Before we start, just look at tables N and O to find symbols for each decay mode. Table N lists decay modes. Table O shows the notation of each decay with mass number on top left, charge on bottom left, and symbol in the middle, and each symbol. Now, when alpha decay occurs, first of all, a helium nucleus is emitted with 2 protons and 2 neutrons, along with a decrease in the number of protons and neutrons. And alpha decay will generally occur because the nucleus is too large, specifically because the nucleus has more than 83 protons. And alpha particles, because they're quite heavy, actually have quite low penetrating power. They tend to be stopped by a sheet of paper, but they still are kind of toxic to cells and tissues. The decay symbol for alpha is the Greek letter alpha, which looks like this, and the symbol is like this, where you have mass number 4 on top left, atomic number 2 on bottom left, or charge of 2 on bottom left, and symbol He to indicate a helium nucleus. And the general equation is, you start off with the heavier nucleus A with mass number X and charge or atomic number Z, undergoing alpha decay to emit 2 things. First off, you emit an alpha particle with mass 4, charge 2, and symbol He, and you also emit a lighter nuclide B with mass number X minus 4 and charge Z minus 2. Alright, and for alpha decay, the new nuclide B formed here is lighter than the original A and has a different number of protons or atomic number. And this is because the new nuclide is relieved of 2 protons and 4 units of mass, or 2 protons plus 2 neutrons, by this alpha particle that's emitted. So 2 protons and 4 units of mass are lost each time an alpha decay occurs, and the new nuclide must be lighter with 2 less protons and 4 less units of mass, or protons plus neutrons, to conserve both mass number and charge on both sides. Okay? Next, when beta decay occurs, a neutron becomes a proton, an electron is emitted with charge -1 and mass 0, and the number of protons and atomic number will both increase. And beta decay occurs because the nucleus has too many neutrons, or the neutron to proton ratio is too high. Okay? And beta decay has medium penetrating power. So it can cross human tissue, but it can be stopped by metals and plastic. And the decay symbol for beta is the Greek letter beta with the minus sign here. And the symbol looks like this as follows, where the mass number 0 is on top left, atomic number -1 on bottom left, and the symbol E indicates an electron. And the general equation for beta decay is you have this nuclide A with mass number X and atomic number or charge Z undergoing beta decay, emitting two things. First off, the first thing you emit in the products is an electron with mass 0, charge -1, and symbol E, along with also, in addition, a nuclide B with mass number X and charge Z plus 1. Note here that the new nuclide B formed from beta decay has one more proton than the original. And the new nuclide has a greater charge or atomic number by 1 because the beta particle has charge -1 with 0 mass. So the new nuclide must be 1 higher than the original in terms of protons or atomic number to conserve atomic number or charge on both sides. Obviously, the mass, you don't have to do anything to it because the mass is the same on both sides already. Okay? Next, we have gamma radiation. And in gamma radiation, a high energy photon is emitted where there's a transition to a lower energy state, so energy is lost. The reason for gamma radiation related to this, to what happens, is because the nucleus you start out with has too much energy, so it must lose energy through gamma radiation or gamma emission to lower its energy. All right, and gamma's penetrating power is quite high. It can cross the body and ionize molecules. It's only blocked by something like lead or something strong like that. All right. And the decay mode symbol for gamma is the Greek letter gamma, which looks like this, sort of like a curved Y. And its symbol looks like this, where you have the symbol gamma with mass 0 in the top left and charge 0 in the bottom left. And notice how the mass and charge are not changing. Only thing you're changing here is energy. Now, the general equation for gamma is nuclide A with mass X and charge Z is energetic. That's what the star means right here. And because it's so energetic, we need to bring down the energy. How does it do that? It undergoes gamma decay here to form two things, a gamma particle with mass 0 and charge 0, as well as particle B with the same mass X and the same charge Z as the original, only this time it's less energetic since energy is released in the form of gamma particles or a high energy photon. Okay. Next, when positron decay occurs, a proton becomes a neutron. A positively charged particle with mass 0 and charge +1 is emitted, and the number of protons and atomic number will both decrease. Now, positron decay occurs because there are too many protons in the nucleus, or the neutron-to-proton ratio is low. Hence why positron decay converts some of these protons into neutrons, so that you can bring up the neutron-to-proton ratio and obviously make it more stable. Now, positron decay is medium in power, much like beta decay, so positron particles can penetrate human tissue, but they cannot ionize or pass through many metals like gamma can. And the decay symbol for positron is beta positive, and the nuclear symbol for positron is mass number 0 on the top left, atomic number or charge +1 on the bottom left, and a symbol E indicates a positron. And the general equation is you start out with the nuclide A with mass number X and charge or atomic number Z undergoing positron decay, emitting two things. First thing you emit is a positron with mass number 0, charge +1, and in addition to that, you also emit nuclide B with mass number X and charge Z -1. Note the new nuclide form B from positron decay has one less proton than the original A does. And the new nuclide B has one less charge or atomic number because positron has a charge of +1 with mass 0. So the new nuclide must be one less than the original in terms of protons or atomic number to conserve atomic number and charge. Note that you don't have to do anything to mass because mass is the same. All right. Now, last we have electron capture, where an electron is pulled into the nucleus with an electron and proton combining to form a neutron and decreasing the number of protons and atomic number. Electron capture occurs because there are too many protons. In other words, the neutron to proton ratio is low. All right, and the general equation is the nuclide A with mass number X and charge or atomic number Z undergoes electron capture, emitting nuclide B in the products with the same mass X and charge Z -1, where the decrease in charge is due to an electron being captured in the reactant, so the atomic number must decrease by 1 for B in the products to make sure charge is equal on both sides. Notice you don't do anything to mass because mass is already the same. It is unchanged by the electron capture. Okay? Now let's identify types of decay in different radioisotopes. For radium-222, if you look, there's an there's an alpha particle here on the product side, so you know that's alpha decay. Cobalt-60 and rubidium-87, you have a beta particle or an electron here on the product side, so both of these have beta decay. All right, for uranium-239, since you start with a more energetic version of this with the star here, and you only release a gamma particle here in the products, you know there's gamma decay. For magnesium, you have a positron here in the product side, so it's positron decay. And finally, for krypton, since you have an electron here in the reactants, you know it's electron capture. All right, that's it. See you tomorrow.